Welcome everyone to the third talk in the virtual workshop on data-driven hydrology education. My name is Emily Clark and I'm the training coordinator at Quasi. Let's see, before we get started, I just want to make an announcement about the training workshop that Quasi has this October, the role of runoff and erosion on soil carbon stocks. That's going to take place at Purdue University, October 20th through 21st. And the last day to register for that training is Monday, September 28th. So if that's something you're interested in, please go ahead and register online. So the virtual workshop on data-driven hydrology education was organized by Venkatesh Marwad at Purdue University and Ben Ruddle at Arizona State University. So Venkatesh, I'll let you go ahead and continue with the introductions for today's talk.
Hi, thank you, Emily. So again, I want to welcome everyone and thank you for attending our third and last webinar of this workshop. And next week, we are going to have the virtual poster session. So today's talk is development of student-centered modules to support data and model-driven active learning in hydrology. And it's being presented by Professor Emad, Habib, Professor David Tarboton, and Professor Upmanu, Lall. So Professor Habib is a professor of civil engineering at the University of Louisiana at Lafayette, and his broader area of interest include surface water hydrology with emphasis on rainfall, remote sensing, water management, and hydrology of coastal ecosystems. Dr. David Tarboton is also professor at Utah State University, and his interest includes surface water hydrology with emphasis on hydrologic information system and data sharing. And right now he is leading a project called HydroShare, which is about collaborative environment for sharing hydrologic data and models. And the third speaker is Professor Upmanu Lall, who is director of Columbia Water Center and professor in the Department of Earth and Environmental Engineering and Civil Engineering and Engineering Mechanics at Columbia University. So with that, I'm going to let Professor Habib start his presentation for today.
Okay, well, thank you, Emily and Venkatesh and Ben, for the opportunity to present. Can you guys hear me?
Yes, we can hear you.
Okay, and is my screen now visible? Can you see my screen?
Yes, we can see your PowerPoint slide.
Oh, okay, very good. So again, thanks for the opportunity to present, and I think you just heard the title from Venkatesh. This is a collaborative project that has been going on for a few years between our three universities here, and later in the presentation you'll get a chance to hear from my co-presenters, David Tarboton and Upmanu Lall. And the funding for this project has been provided by National Science Foundation, and some additional support was also provided by the Louisiana Sea Grant. Now, before I start, I would like to acknowledge the team members who contributed to this project, either from our universities or from outside collaborating institutions. And many of them are students, grad students, and undergrad. And I would like in particular to dedicate this work and presentation to the memory of our colleague and friend, Yushin Ma. She passed away last week. She was a co-PI on our project, and she contributed a lot, and we'll miss her. Just to identify some goals for our webinar, what we want to get out of this, or at least what we want to deliver. We want to introduce our development, the HydroViz system, and the modules that we developed to support active learning and hydrology education. And our focus is mainly on undergraduate hydrology education. And we also want to hopefully encourage you to adopt HydroViz, the learning modules that come with it, and maybe consider other similar approach also. And the last part of the slide, we'll try to share some of the evaluation results that we learned from the project, focusing on the bigger picture and not going into very detailed results. So just a little bit of background on what motivated us to do this work. I think we have heard quite a bit of justification for the need for reform for in undergrad hydrology education from the last two speakers in the last 2 weeks. I'm just kind of sharing with you some more thoughts on this. We as a team believe that, and I think the community shares that vision too, that there are some certain problems with how hydrology education is being done. For example, the traditional approaches that are followed today focus a little bit too much on unit processes and emphasize perspective knowledge and the use of hypothetical examples. The dynamics of hydrologic and other processes are rarely introduced in any formal way, and the current curricula do not promote the holistic understanding of overall context and how hydrologic analysis can be pursued using data and modeling frameworks. So we basically need to improve how we prepare the future workforce to pursue emerging science-based hydrologic research and applications. And I list here some key elements of this science agenda that has been defined by the community, which we would like to prepare our students to be able to tackle these different issues and needs. So the solution that we proposed in our project and tried to implement over the last few years is basically a solution that is based on an active learning approach. And active learning is a very wide field of educational research, but we would like our approach, or at least our modules, to have the following attributes. We would like to see that the modules can leverage emerging advances in hydrologic research and practice, that the developments to be situated in actual hydrologic systems, driven by real-world context and problems, use recent technologies that provide high educational values, such as web-based techniques, and is most importantly is informed by well-proven theories on and research on effective learning strategies and learning environments. We believe this approach will allow us to introduce context-based introduction of basic theories when they are needed in problem solving, and also it will engage today's students who are more motivated by a desire to contribute to solving societal problems. Just a few words on what is active learning. Like I said, active learning is a very wide field of research and education, and these are just some keywords I want to share with you so that we are on the same page when we refer to active learning. Basically, active learning, according to the literature, is anything or any strategies that involve students doing things and thinking about the things they are doing. It focuses on student engagement, student exploration of their own ideas, their own attitudes and values. It puts a very little emphasis or de-emphasizes the teacher-centered approach where students receive in a passive mode, and it puts more focus on developing student skills through a student-centered approach. It's interesting to know that a lot of these ideas are not really new. A lot of many old civilizations realize that people learn by doing, and I invite you here to read some of these interesting quotes. Tell me and I'll listen, show me and I'll understand, involve me and I'll learn, and this Asian proverb also, which emphasizes the same thing on learning by doing. And the recent literature research also tells us that active learning works or is effective, at least for the most part, if it's done right. And I include here some papers and slides that show that, and I'm not going to go into the details. I left them there. I know the webinar is recorded, so if you are interested, you can go back and check some of these papers and some of them are very interesting and very informative. So coming back to our own project, we started with this notion that we will use actual ecosystems or actual hydrologic basins. So we picked 3 here, one in coastal Louisiana, and the second one in the Rocky Mountains, Utah, and the third one is in Everglades, just because the team has expertise in some of these sites. And we wanted to develop learning modules that are situated in these ecosystems that are driven by data resources and model and simulations. We use web technologies to be able to package these into something that attracts the students and build those learning modules. At the bottom here, I show some of the themes that will be the subjects of these different modules. Some of them are on surface water runoff, and others deal with climate teleconnections, and some other modules also will deal with how sensitive the interactions of natural and human systems. And then we put those into an implementation mode in the classroom, whether it's a different classroom, different courses at the same curricular level, or we also try to touch on maybe some of the freshman courses with a little bit of introductory materials, and maybe also help the introductory graduate courses by some of these modules. And then we go through a cycle of evaluation and assessment where we look at how useful these things are they effective or not, did they result in an improvement in student learning, can somebody else use these, and what the feedback is. And then that feeds back into the loop of program revision and modifications, whether to the system itself or to the content, and the cycle continues. So it's a loop of development, improvement, evaluation, and assessment. So we tried also to identify some components of what the literature says a good active learning module should have. And these are some very general ideas that we think are applicable to hydrology. So a good active learning module in hydrology, we would like to have a definite beginning and ending. It has a clear purpose or objective. It contains complete and understandable directions, and provides feedback and mechanism to the user, and include a description of all the tools that are being used there. And we tried, we translated these components into a set of questions that guided our design, and I list them here. Basically, will the students be able to complete these activities independently on their own, meaning without the help of the instructor to some extent? Well, if they need help, will the system be able to provide them with that guidance, and what form is that? And also, does the system provide any self-evaluation? Can it have any formative and summative evaluation? And also provide some support to the instructors so that they can adopt these material and use them for their own classes. So moving to the site itself, I'm going to now show you an overview of the development that we made, and then I'll turn it over to Manu and David to show some examples of the modules that we developed. So the site is actually located at this address. I'm going to switch to a website here, and hopefully everything will work fine. So this is the homepage of the project, and that's basically where all the modules can be accessed. Each module is represented by a marker, and as you can see here, we have several modules, one in Utah here that focuses on flash flood protection, and several in coastal Louisiana that focus on coastal restoration issues and hydrology of coastal systems, and one that is focused on climate teleconnections, and it has an application in Florida, even though the scope is really regional and global, if you think about it. But we just chose to associate it with Florida because it has an application there. And the user will, or the learner, the student will start by clicking on one of those. So I'm going to show you an example here. And there's a blurb here provided by the system, and you proceed to read a little bit more about it. And if the student is ready to actually interact with the module and work on it, they can click on that, and that's when the system will open a new browser, and in that new browser will be the home page of that particular case study, or that particular module. So this home page here, or this page here shows the modules that are hosted in coastal Louisiana. You can switch between different modules or case studies. So we are having 4 here. We have a couple more that we are still adding. So if you choose to work on one of them, that's what you do here. And the interface has 3 parts here: the table of contents. It has a lessons tab. It has a map tab. The map tab here has standard navigation tools. You can switch the base maps and that you want to work with, depending on whatever makes most sense to the user. And it has also some set of GIS layers that the user can interact with, and that are mostly relevant to the module. So you can toggle these on and off, and look at, for example, in this case here is the vegetation types and in the ecosystem and so forth. So that's what the map here, and this particular module has a set of output simulations, model simulations that come with it, so the user can also interact with those. We build this into the system so that you can, grab out some data, that was generated for this site, and you can customize your download of the data between scenarios and dates and variables and so forth, depending on, what the modules will tell the user to do. And on the left side here, you have a set of table contents, basically, that you can expand and collapse, and that's what's being displayed here on the lesson. And each module is divided into certain sections, and each section has its own subsections with learning objectives defined up front. And then it has a sort of kind of background information. A lot of it is interactive, where the user can read a little bit about maybe here in the case, introduction to the ecosystem itself. They can interact with the map as they read the lessons, or visit some links, or interact with some images here that shows some certain features. And when they are done with that section, they are ready to take a quiz, some sort of a quiz here, where they answer questions, multiple questions, and then at the end, they submit the quiz and they get a feedback there. We embedded a lot of help to the students here in terms of, some relevant sections that they can go back to, and relevant layers on the map that they can activate and see how they can answer these questions. When they are done with the quiz, they can also move to what we call learning activities. And this is like really the bulk of the learning course here, where we design these activities, quantitative activities that deal with data and model simulations, whatever the case study applies to. And the student goes through, just a procedure of, instructions, and it has some sort of help also, whether it's a video, a screencast that illustrates a certain procedure that they could not do, or they want a little bit of extra help on. Sometimes we'll put like templates for Excel, or some sort of template to help the students implement some of the activities. It had also some intermediate feedback, so the students can figure out whether they are on the right track or not, without pursuing too much and making mistakes that they cannot recover from. And the interface proceeds in the same way, for the different sections, where we keep that structure consistent, where when they work on different activities, different case studies, they get familiar to the system, and it builds on the previous sections. So, like I said, I'm not going to go through a whole lot of details on every one of them. I hope I was able to give you an overview of the structure and the different attributes that support the learning of the student. And I would like to turn it over now to David Tarboton to maybe give us a little bit more detailed about one of the modules, which is the Lobe and Dry Canyon flash flood. And then after David, Manu will also do the same thing for the climate teleconnection module. And I'll try to close after that with a few slides. So David?
So thank you, Emad. I was really excited to get involved with this HydroViz project, and be able to start developing content to use in the engineering hydrology class that I teach. Emad, you're going to need to stop sharing so that I can share my screen.
Sure, I just did.
Okay, there we go. So you should see that. So I was responsible for this module in the Rocky Mountains, Utah, designing a flood protection system. So the approach that we took was a problem typical of what engineering hydrologists might face. We wanted to try and introduce to students the learning they needed by actually doing the hydrology for the design, and we wanted to introduce essential subject matter just in time in the context of solving the problem. So this was an effort to try and apply some of the concepts that Emad just spoke about in terms of the problem-based learning approach. So the setting that we chose to work is Logan Dry Canyon, which is just on the east side of Logan, where Utah State University is. It's a mountain watershed upstream of encroaching urban development. It's representative of probably quite a lot of the western U.S. The city recently constructed a detention basin at the place of that little dot there at the outlet, and a stormwater drain that goes from that location down to Logan River. So the question posed is, what if you, as a student doing my hydrology class, had been the design engineer responsible for designing this flood protection? So if you can actually zoom right in on Google Earth, and you can see there is the detention basin that's already built, and this is a photograph of it. And you can see that the houses have sort of come right up to the edge of where the mountains start getting steep. So solving the problem requires quantifying catchment properties. It requires quantifying precipitation. It requires calculation of runoff, the runoff generation problem. Then it requires computing the hydrographs. Once you've got the quantity of water that's involved in runoff, what is the lag, what is the timing, what is the unit hydrograph involved? And then it involves going through the design process of, okay, so what's the size of the storm drain? What should the size of the detention basin be? What are the options involved? So it actually goes all the way from fairly basic hydrology to solving an engineering problem. So you can see on the right, this is the table of contents of our HydroViz module and the sort of mapping of the concepts that we wanted to cover onto the various pieces of content. So let me see if I can bring to the front of the screen here the actual module. So you're seeing the HydroViz display now. You can actually zoom right in, and there is, if I zoom in a little bit more, there is the detention basin that I was just showing. So the students are getting a sense of what the setting is, and in terms of going through the contents of the module that Emad just showed. We can look at the first activity is quantifying the catchment properties. So there's a bit of a background for the catchment, but then in the learning activities, we actually take the students to the USGS StreamStats site, and we guide them through the step-by-step process explained in detail here, where at the end they will have delineated a watershed. So the point is to learn about watershed delineation while looking at it in the context of their problem. Then one of the next things we wanted to do is examine the precipitation that might be involved and come up with a design storm. So moving down onto the section on precipitation, first, how is precipitation measured? So one can read a little bit about sort of common rain gauge technology and the sort of things one has to do with precipitation data in terms of area averaging, perhaps using teaching polygons or perhaps some sort of surface fitting approach. And then eventually they get down to the section on hydrographs and design storms, and we take them through the approach of coming up with an alternating block design storm. So we show how you've got a depth, duration, frequency curve, and you can then construct a design storm. And the learning activity has them actually go to the NOAA precipitation data frequency website and end up downloading the data and coming up with a 100-year design storm for this particular setting. So once you've got precipitation, the next section in the module here is runoff. So how much of that infiltrates, how much of that runs off. So it requires knowing things about the soil properties, the runoff generation mechanisms, green amped infiltration, and so on. So there's a section here, and I think it was where we go through a fair bit of the background on runoff generation processes, and then we lead them through the calculations for actually applying the green amped method. There's a video cast on going through the detailed calculations involved in using the green amped approach. So then at some point we get to where, well, the students have learned the basic calculations, but a design engineer is likely to be using a model like HEC-HMS for doing this design. So we introduced that, and HEC-HMS has the ability to calculate infiltration using green amped, and it has the ability to end up producing a storm hydrograph from rainfall. So we guide students through, if you don't have HEC-HMS loaded, where you can get it. We point to the standard HEC-HMS user manual material, and then at the end, they end up with the precipitation hydrograph that was calculated earlier and the design hydrograph. And now they've got the inputs that are needed for designing the flood protection system. So we go into a little bit about how detention basins work. So there's information on a detention basin really chops the peak off an inflow hydrograph, reducing an outflow hydrograph. And then we lead them through the learning activity of actually applying HEC-HMS, coming up with the dimensions of a detention basin, the properties of the outlet, and evaluating some options to come up with a design. So let me minimize that. I had slides that went through all of that just in case the demos didn't work. But in terms of designing flood protection, they'll be learning to trade off the peak reduction based on detention, storage, and outflow properties, evaluate the design parameters for that physical setting, and use HEC-HMS as a design tool, having just learned the principles that the model is applying sort of in the context of this setting. So the result is a practical solution similar to something that's actually been built. And along the way, the students ended up learning about precipitation, learning about infiltration, learning about some of the statistics in terms of design storms, learning about runoff generation and unit hydrograph modeling with HMS in the context of this problem that they can actually, at least for students at Utah State, can go and walk around and see. We've got quite a few photos on the in the module so that people who are not local can
but I got kicked off.
sort of get a sense of what the
Okay, can you hear me now?
Going there. So I think now is where I turn over to Manu.
Okay, so I can use the, I can work with the main PowerPoint file that people are using. Or I can share screen,
All
either
guests
way.
have been unmuted.
Manu, are you on the line?
That may be
Okay.
faster, I think.
Yes, we can hear you.
Okay, perfect. So thanks very much, David and Emad. I'm a minor player in this project, and the main thing that I've been interested in is, as perhaps everyone knows, there's increasing recognition amongst the hydrology community that integrating climate information into hydrologic analyses is something that we have to figure out a good way to do, particularly in the undergraduate curriculum. And the specific thing we try to do here is to provide that introduction through climate teleconnections rather than a very large module that would look at ocean atmosphere dynamics and climate change and come through there. So what I'll try to do is to show you guys a little bit of what we've put together, and the emphasis is on taking a data-driven approach to getting this information across, rather than getting a lot into the theory of these things, because the time to introduce this information in the undergrad hydrology class is a little bit limited. So that's the thrust. And then what we try to do is to point out that if you're concerned about, for example, changing climate conditions, then understanding how the regional hydrology could be influenced by changes in regional precipitation and or temperature relative to what is going on globally is of interest. So we focus this on connecting the student to global data sets that are available for precipitation flow and other variables, and a system which allows them to bring in their own data as well, so they can explore whether, for example, in El Nino or La Nina years or other climate regimes, there is a significant change in the kind of events that they experience there. And also looking at forecasts from climate models, either for a season or deep into the future, and evaluating whether those are useful or not in their context. Let's go to the next one. So here, I think given that Emad already showed you the structure of some of the modules, I've just provided a link so that people can do it offline and not spend time there. So here are the climate mechanisms we educate them about. There are the El Nino Southern Oscillation, the Pacific Decadal Oscillation, the Atlantic Multi-Decadal Oscillation, and the Madden-Julian Oscillation. And the key thing here is that these are things that influence regional hydrology in different places in the world in different ways and at different time scales. So for example, El Nino is a 2 to 7 year phenomena. The PDO is a 16 to 20 year phenomena, and the Atlantic Multi-Decadal Oscillation has 2 to 8 year components, but also largely greater than 40 years. So you could have 40 years wet and then 40 years dry, kind of is the idea. And the Madden-Julian Oscillation is actually a 30 to 60 day phenomena. And so these combined have different effects on regional hydrology. And in this particular slide, I'm just illustrating the kind of information they get, explaining what the phenomena is about in terms of the dynamics of the phenomena, On the left, you see the 3 slides with El Nino, La Nina, and neutral. So there's narrative in the slides explaining how the system works. And then on the right-hand side, you're seeing what people typically understand about the extreme endpoints of the impacts of these phenomena on different variables. So this kind of information is presented in narrative form and connects to a bunch of links where these things are explained. So let's look at the next slide. Yeah. So then what they can do is that we have hooks into 2 major climate databases. One is the KNMI Climate Explorer, and the other is the IRI at Columbia University, which has an extensive data library. So what's available in these data libraries are historical climate data, atmospheric pressures, temperatures, rainfall worldwide, and these are accessible so that you can take your location and explore how those global patterns or national patterns relate in different seasons or any actually time interval that you want to what is going on globally. So basically the idea here is the student is then walked through a guided analysis of those teleconnections, first in terms of what is generally expected in different parts of the country, and then specifically for your time series, do you actually see those relationships? So the analyses that the student does at this stage are correlations and also composites. So composites here mean looking at an extreme phase of El Nino or La Nina and what that corresponds to in their context, or choosing the wettest years or driest years in their own record and seeing what the world was doing at that stage. So let's go to the next one. So here's an example of that sort of analysis. So on the left panel, we can pull up the entire United States precipitation fields, for example, look at the seasonal or for even a calendar day averages, standard deviations, coefficient of variation, and then the place you are in is put in context. So in this example, we are working with the Everglades, which is right about there, and we can pull out the time series associated with that location for a particular station or for a space average of those stations. We can have the student do correlations with sea surface temperatures in the preceding season. And in this example, it is nice because we see that the previous season sea surface temperature is quite nicely correlated with precipitation in that season in the Everglades. So you could essentially have a predictive model. And that's confirmed by looking at the sea level pressures also. And there is narrative there explaining why higher sea surface temperatures here would correspond to lower pressures and to higher convection, which then becomes a moisture source for the Everglades, how that thing can come through and then have an impact there. And similarly, we can on the bottom left or the middle bottom look at what climate models are forecasting for the upcoming season. And in Florida, you see that the skill of the model in terms of the correlation of the model forecast precipitation and what is actually observed subsequently is quite high, and that the source of that information is the sea surface temperature and the sea level pressure configuration in the previous season. So they get an understanding of both the correlative analyses, but also what is driving that system and why those correlations make sense. So let's go to the next one. So as part of this, what we are also getting them to do is an understanding of what is meant by skill in models and partitioning what is meant by bias and variance. And this, so this module allows them to go through historical data, look at the long-term averages, and hence see what is the consistent bias in the model for a particular variable for a particular season. If you remove that from the picture, then explaining the rest of the scatter as a standard deviation or uncertainty, and then pointing out the role bias and variance have in terms of evaluating predictive skill. And then we also show them that, okay, if you believe that this is based on essentially El Nino information, then what is the predictions from the variety of different climate models? And in the bottom left, what you're seeing is a bunch of physics-based models and then a bunch of statistical models that forecast El Nino. And typically, these forecasts are available for the next 18 months, so they can get a sense of what kind of uncertainty is there just in the climate model, in the mechanistic aspect of it. And then if you look at El Nino versus your own precipitation, you can get a sense of what part of the uncertainty is due to that. So to sum up, the idea here is to get the students introduced to some basic levels of climate information and how to physically interpret them and to mathematically manipulate them, so that as they look at, for example, water balance analyses in the class or risk analyses in the class, they have a way to start doing this. So what I haven't shown here is a module that actually builds some capabilities for doing those kind of things using regression and conditional simulation models. But hopefully that gives you a sense of where we are trying to go with all these things. And the same applies to if you're looking at climate change analysis. So that's the climate teleconnection module. It's back to Emad.
Okay, well, thank you. Thank you, Manu and David. So I'll try to wrap it up here in the next few minutes or so to give time for questions. And I guess I'll share my screen again. And okay, so I guess I'll you know, we have several other modules, you know, from coastal Louisiana, like I said. I'm just, you know, I'm not going to introduce those, of course, for the sake of time. And this slide here just provides you with the titles of these modules. They are place-based, they are problem-based, but the way we design them, you know, we think they have, you know, a much bigger impact beyond the place or the problem that they deal with, so that they can appeal to students from other locations as well. And they mostly revolve around the impact of human interventions on the natural system and how we can reverse some of that negative impact through restoration processes, restoration activities, and what kind of negative impact that you can cause as part of that. So, and along the way, the student learns a lot about, you know, hydrologic processes, the impact on the ecosystem, and some data analysis, and interacts also with the model output. So. The next few slides provide a little bit more details about each module. You know, I'm going to skip those and leave them in the PowerPoint that will be posted online. If you are interested, you can go back and learn a little bit more about it. But the website also provides a lot more details than that. But I would like to spend the last, you know, maybe a couple minutes or so sharing with you some of the experiences that we, you know, had doing this project, you know, mainly through the assessment effort. And again, I emphasize here that this was really an essential component of the project because, you know, doing this assessment through an iterative loop of implementation and evaluation and improvement is really what can make a big difference in terms of making your module effective and useful. So that's not just something that's done at the end and you say good or bad, you know, have the assessment guide the evaluation. And these are the guide the development, and these are some of the approaches, the assessment approaches we followed. You know, there is this model evaluation called improvement focus. So the focus is on improvement of your development, and also a mixed method research approach where you try to identify what works and what doesn't work in your development and why it's not working and what you can do to improve it, and integrate the feedback from the different users, whether it's the professors, the instructors, or the students. So with that, we formulated some goals and questions for our assessment. And again, I'm not going to go through the details here, but the headlines is we want to evaluate the stability of the program. Are we staying, you know, honest to what we promised in terms of developing these modules and their attributes? How effective they are in terms of usability. So this focuses more on the system, on the software, on the interface. and effectiveness in terms of impact on student learning. Did they learn or not? What interfered with their learning? What their attitude towards the module? Did they find them engaging or maybe tedious or overwhelming? And finally, also, can these be adapted in other settings, whether different classrooms, different instructors, or different institutions, hopefully? We gathered a lot of data to try to answer some of these questions, and again, I'm not going to go through the details here. What I would like to share with you some overall lessons that we learned from the evaluation. Again, this is an example of a detailed evaluation study that we did that compares, students from different universities and how they were able to learn the material through set of objectives and so forth. The following point is really what I want to impress upon you from the students, interviews and feedback that we got from them, what they like the most from the development. They told us that they like that the modules are based on actual real-world hydrologic system and problems, that they are situated in places outside of their immediate locale. So there were some students who said, no, I just relate to where I live, but many of the students related to the fact that this is coming from Utah, that they never visited, and that was exciting to them to know that the same problems apply here or there. They also like the fact that the modules were developed using a web interface. They like that. They feel excited about it. The interaction of the maps, and also that the system provides feedback and self-assessment. And they actually, whenever an activity lacked that, the students suffered, and the feedback was saying that we get stuck and we don't know what to do, or at least we need some help. And also, this is interesting that some of the students find this interesting because it provides opportunities for independent work. Basically, students like to take control of their own learning. They want to do things on their own and find things without the intervention of the instructor. At least they feel that they are empowered and they learned a lot more than being, told what to do. And the last slide I have here is basically what we called a recipe for active learning in hydrology. I'm sure others will have, more ideas, to this, similar to this, but the slide here will share with you some of the components that we, at the end or as we go through the project, we identified to be, some key elements for a good learning, active learning module in hydrology should have, So we learned that, of course, the module has to be structured around well-defined learning objectives and outcomes. You also it should have quantitative activities that support higher-order thinking skills. It should be based on real-world problems with real-world hydrologic basins and data. It should support students' ability to transfer their knowledge and learning skills beyond, the same location of the module. This is also important, that the module or the active learning module should go beyond just data access or visualization, which are important, of course, or procedures to, analysis and synthesis of these data. It should link to hydrologic resources from the community. There are a wide range of resources there that we need to tap into, and they should have a strong content in the technical subject that it's covering. So it's not just a procedure or a superficial coverage of the subject. And adequate background on tools, data sets, models, sensors used. And like I said, this is something we learned from the actual project is that web is very attractive to students, interaction with maps, and the support and feedback that the system can provide that can make a big difference in terms of the effectiveness of a certain learning module. So I guess with that, I'll close here and I'll leave it, I think we still have, a few minutes for questions and answers, and we would like you to consider adopt some of these modules, maybe visit the website and learn a little bit more about it. And if you have ideas to contribute to module, we'll be glad to talk with you about it and share some of the resources, whether it's templates or codes or just overall design guidelines. And I guess I'll stop here and take any questions, if the audience has.
All right, great. Thank you so much, Emad, Manu, and David. At this time, we will take questions from participants. So if you do have a question, go ahead and type it into the chat box, and we will relay it to the presenters. So while we wait for questions to start coming in, I do just want to remind everyone that next Tuesday from 2 to 4 p.m. Eastern Time is going to be the virtual poster session on data-driven hydrology education. You can use the same link that you used to connect to the webinar today, except that, again, it is at a special time, 2 to 4 p.m. And we are going to have 5 abstracts presented and then a short presentation from the Quasi Water Data Center. So it should make for a really great virtual poster session. The idea being that the poster presenters will spend a few minutes explaining their poster and then kind of open it up for some more discussion and interactiveness than just a normal webinar. So we hope that you will be able to join the session next Tuesday from 2 to 4 p.m. So we have a question that came in from Blake Landry, who says, very nice presentation. If an instructor wanted to start developing modules for HydroViz, how involved is this process?
Okay, yeah, well, I'll try to take a stab at that. I think the process is a little involved, so I wouldn't say it's something that can be done, quickly. However, our team can, like I said, share some of the resources that we developed as part of this project. But it always starts from developing the contents of the module itself, whether it's the background that the student needs to learn before they can delve into the learning activities, and more importantly, the learning activities themselves, and the feedback that the module will provide. So these all need to be developed by, like, the author of the module itself, and some of these modules, just to give you, an idea about how involved they are, if you type them in a Word document, they come up to, like 10, maybe several tens of pages, maybe 20, 30, 40 pages, depending on how involved you want it to be. Now, what the interface and so forth, we think we have, a system where we can plug in some of the content if they are prepared by an author, if they are prepared in the same format where you have the background, the quizzes, the learning activities, and the supporting material. The integration into the web should not be that involved. We can do it if the person does not have the expertise. If they do, we can certainly share the code that we developed, or at least we can talk with the author about that. So, Manu and David, you were involved with me all along. I don't know if you have anything to add to that.
I mean, well, let me just say, right now at this point, I think it's effectively a custom website. We don't have it in the form that it's a sort of a general purpose content management system that anybody could upload content to. That would actually be a really cool thing to do, but it'd be a whole nother project.
Okay, there's another question from Jim Nelson. What is the long-term maintenance plan? Tools and data sets change so quickly. How can you evolve that?
Yeah, well, that's a good question, and I don't know if I have the answer to it, but we tried all along to not reinvent the wheel here. So in terms of if there's a data set out there that we can, use, we'll link to it and we'll use it there. So, and sometimes there are custom data sets that are generated by the specific module that we post there. So, so I guess, by just linking to these community resources, we can ensure some longer term continuity. I know, David, you might have some ideas on that. I know that you do a lot of, that work, and we talked about it in the past, with issues with data sets and data sharing and so forth. So,
so we did think about whether we could get the data into, for example, a quasi hydro server that we could then access it from that. Right now, we've the data that we're using in the modules is sort of custom canned, but I guess we had a lot of discussions about ways to expose students to just the real content of what the real world is out there, so that they can learn from that. And I think the answer that Manu's written is basically in that spirit. The climate data libraries are continuously being updated, and so that we'll support the module.
David, you have 2 questions there for you.
So you want me to do the one with, so from Tim Eaton, so the question about the Utah retention basin. So HEC HMS is a model that comes from the Army Corps of Engineers. It is free for anybody to download it. So yes, the instructor and the students do need to get that model, but it's just minutes to download and install on any PC, and there's lots of guidance on the web for how to run HEC, but it is something that you actually have to download and install. So how long do the steps for my exercise take? I'm going to say we typically break it into 3 parts, and the students have about a week for each part. So we set the first 2 sections as the first assignment, the third section as the second assignment, and the last section is the third assignment, so 3 weeks.
Yeah, and I also would add that every module online, if you go there, it will have some description of how much we think, how much time we think it would take for the student to complete. So we try to provide an estimate for, how long each module should take, and also we provide there some sort of rubrics, so that the instructor can know what the students are supposed to do, and also the rubrics will be made available to the students. They are available online. I guess the last question here is, I'm very excited. Okay, well, thank you. Yeah, I mean, this is quite an effort, and we have actually plans for, I have a couple more modules in coastal Louisiana that are being, implemented. They are not online yet, but we finished the content, and they're more on hydraulic type analysis using HEC-RAS, for example, if your classes are interested in that. And we do have plans to continue doing that. Maybe I know David also, might have some other modules developed. Our project is probably getting to an end in the next year or so, and we would like to focus more on, assessment and, maybe getting some of these modules out there, being adopted by others and getting feedback from them. And maybe after that we can think about a bigger community effort where we can involve more people in developing these modules, and maybe improving on the system itself depending on the feedback that we get, to address some of the issues with the data sharing and accessibility to data and maintenance and so forth, which are very important.
Thanks very much, Emily, and
anyone
Emad
else has a question? Now's your chance to type it in quickly.